Welcome back to a new video about circuit analysis using Fourier series. This is our example number 8. In this example, we will again look at a circuit where we apply a non-sinusoidal signal, and we will carry out the calculations for the necessary requirement, and we will simulate in this example to verify our calculations, and the simulation will be done in SPICE. So let's look at our example number 8. What we have is the following situation. We have the Vin, which is shown here. So the waveform Vin will be applied to this circuit, which is a RL circuit. Its values are given, so the inductor and the resistor values are given. The output voltage, what we want is the output voltage of this circuit and also the total harmonic distortion. So we will calculate these using Fourier series, and we will also simulate the circuit in SPICE to verify our calculations. What you see as an additional info for this example, that this circuit will behave, of course, frequency dependent. You can see that the inductor will be a short for DC. That's just the reactance of the inductor, which is omega times L. If the frequency goes up and at infinity, approaching infinity, that will be of course an open, so it will be blocked actually this input. So the input voltage will be at the output in total when this is a short at DC, and it will be blocked totally when this is an open. That will happen at infinite frequency. So this is actually a low pass filter, so it will block the high frequencies. Okay, let's move on for calculation of the output signal. So what is the situation? Before we move on, we need to of course determine the Fourier series representation of this input signal. For that we can use the table. In the table you can find that the amplitude and also the period, capital T, will be given in a general form. So the square wave, which has a fundamental frequency 2 pi over the period, will be of course calculated by using this given signal. So it is 2 pi over that 0.001, so 1 millisecond, so it will be 2000 pi radians per second. And the A, that is the height of this waveform, that is this, and that is in this case 1. That means actually you place 1 here and you place 1 there, so 2 times 1, and you place your n times that omega 0, which is 2000 pi radians per second. And then your waveform is actually complete. This is of course general form, so our solution says the Fourier series of this signal will be 1 over 2 plus 2 over pi, 2 times 1 over pi, and times the sine, the summation of the sine n omega 0, which is the fundamental frequency, t divided by n in volts. And n will now be given by 2k minus 1, where k will be 1 all the way to infinity in integer form. That means n will be 1 for k is 1, but it will be 3 for k is 2, and it will be 5 for k is 3, it will be a 7 for k is 4, etc. So you can see that this input voltage will only have the odd harmonic. So we have the DC term, and these are the AC terms, and if you look at the n, you can only have 1, 3, 5, 7, 9, 11, etc. So you can see that the odd harmonics will be present in our Fourier series for the input voltage. So the fundamental frequency, the fundamental period again, capital T of this input signal is 1 milliseconds, thus that means T is 1 milliseconds. The radian frequency was given by this one, and if I do the math here, you will get for the omega 0 2000 pi radians per second. Or you want to have it in hertz, you can do F0 will be 1 over that period will be 1 kilohertz. Thus then we have the following expression. If you just substitute for the omega 0 the given value, then we have the following situation. Again, the n is given by 2k minus 1. So that is what we have. If you of course want to use this expression in a cosine form, which is the reference where we use as we move on to the complex plane, to the phasors, then we of course need to rewrite the sine in a cosine waveform. Then we have to subtract the minus 90 degrees. So if you do this, so you want to write down your sine waveforms in a cosine, then this term must be added by a minus 90 degrees. Then this expression will be exact same as this one. Okay, so let's move on. What we have in the following is then the situation where we want to calculate what each term will do. So the input signal, again, this is given by this expression. We have determined this. So if you work this out for several terms, you will see the first is just a DC and it's given in pink here. The amplitude is given by 2 pi over n, and then the cosine of the 2000 pi n t minus 90 degrees. And if you move on, for example, this for n is 1, and this for n is 3, you can see is 3 here, it will be in the denominator, and this will be of course 6000 pi, you can see that here. The phase will be again minus 90 degrees, so that doesn't change. And it will be for n is 5 in a similar form. You will have 2 over 5 pi and then a cosine of 10,000 pi, so it's 5 times this 2000 pi t, and it will move on to the next harmonic, so it will be 7th harmonic, etc. So you can of course move on to many terms if you want. This is just to give you an idea how the expression will look like for the DC term and for the first 4 harmonics. Now if I just collect the terms here, just to give you an idea what's going on, this was the k, which was given in the summation of the expression, and this is then the associated n. So if the k is 1, the n is 1, the k is 2, n is 3, k is 3, n is 5, k is 4, n is 7, using this formula. The frequency is 0 kilohertz, which is of course this is just DC. 1 kilohertz is actually when we have the first harmonic, which is actually just the fundamental frequency. And 3 kilohertz, 5 kilohertz, and the 7 kilohertz are all harmonics. What you see is at DC, you can see that the expression for the input signal is 0.5 volts. So that means this is 0.5 volts. The phase is 0 degrees, so there's no phase orientation here. The amplitude for the 1 kilohertz for the first harmonic, fundamental, is 2 over pi. This is the amplitude, but the phase is minus 90 degrees. This is actually also shown here. So this is actually a table nicely done using the frequency, magnitude, and the phase. You can see all of them in one picture. The 3 kilohertz is actually the following harmonic. So this is actually where we have the n is equal to 3. Then the amplitude will be 2 over 3 pi, which is also shown here. And the phase will be again minus 90 degrees. It will stay the same. And if you move on, it will be 2 over 5 pi, 2 over 7 pi for the next harmonics, and the phase will be again minus 90 degrees. This for the input signal. So what is then the low-pass filter circuit transfer function? Because this will be applied to our RL circuit, which will be of course a low-pass filter that will of course has some dynamics, and that will produce the output signal Vout we would like to determine in time domain also. So this was the circuit we have given. So it was 400 millihenries and 2.5 kilo ohms RL circuit, low pass filter. We have applied this input signal to this, and we would like to know what the output is. So using phasors and also the voltage divider rule, we get the following expression for the low pass filter for this circuit. So H is equal to the Vout divided by Vin, all in the frequency domain. You can of course have then R divided by the total impedance, so R divided by R plus the X of L, which is the reactance of our inductor. Now if you work it out, for the reactance of the inductor will be J omega sub n L, and J omega n will be of course n times the omega 0, which is the fundamental frequency. Then you can find all the harmonics in here. And if you now just substitute the values, 2500 for the R and also here, and you can see that will be n J n times 2000 pi just for the omega 0 and 0.4, 400 millihenries for the L. Now, if you simplify this a little bit, you will have this expression. Now, this is of course the transfer function of our low-pass filter in the complex form. We would like to know the magnitude and also the phase. So for the magnitude, I have this expression we'll use later on to further calculations. And the phase, the argument, is this expression. So how do I come to this expression, which is actually this length, so the numerator length divided by the denominator length is the length of your transfer function h, which is actually shown here. The argument, which is the phase contribution, is the phase of the numerator minus the phase contribution of the denominator. Now, phase contribution of the numerator is 0 because it is a pure real expression. The phase contribution of the denominator is determined by the real value and the imaginary value. So the real and imaginary value, since the imaginary value will change as n changes, the phase will be changed, and that's given by this. So this 0 degrees minus this, and this minus is actually from the denominator, and the arctangent will then produce the required phase. The real value divided, the imaginary value divided by the real value. And if you simplify this, you will have minus arctangent 8 pi n divided by 25. That's what you have for the expression for the argument, and this is the expression for the amplitude or the magnitude. Now, if you collect the terms again for case 0, 1, 2, 3, 4, etc., and also for the associated values for n using this formula, you can see all in the similar, exact same frequencies. So DC fundamental, first, second harmonic, third harmonic, third harmonic, fifth harmonic, and seventh harmonic. These are the values. Well, if you do the math here for the values of n, for n is 0, this is just 1 for the magnitude. And if you do n is 3 or 1 first, then you will have 0.705. For n is 3, you will have then 0.315, etc. for all values for n. For this case, the first 4 harmonics, including the DC value. The phase will be for this expression, so you calculate the phase using this expression. This is the argument of that low-pass filter. If you do n is 0, that will be 0. If you do n is equal to 1, that will give you minus 45 degrees approximately. If you do n is 3, it will give you approximately minus 72 degrees. And if you do n is 5, you will get minus 79 degrees. And if you do n is 7, so it is 8 pi times 7 divided by 25, then you will get very close to minus 82 degrees. In this case, I have then the table for my low-pass filter circuit for the magnitude and also for the phase for the associated frequencies. So I have actually a similar table generated for my low-pass filter also. We will use these two tables to generate then the output signal. So let's look at our next step. This was our input signal again, expression. And this was the table for the input signal. Now the output signal, output voltage, will be just the filter expression, low-pass filter transfer function, times the input voltage, both in the frequency domain. So this was the low-pass filter. Again, to memorize what we have discussed in the previous discussion. For the magnitudes, for the V out, I need to calculate or determine the magnitude of my low-pass filter and also the magnitude of my input voltage at the associated frequencies. So what I mean is the following. At DC, I have a gain of 0.5, amplitude of 0.5 for my input, and the gain is for my low-pass filter 1. So that means 0.5 times 1 will be my DC value of the output voltage. So this is actually shown here. This for the 1 kilohertz for the first harmonic, the fundamental. In the similar form, I take the 2 over pi times the 0.705. That's actually shown here. So this is the gain of your low-pass filter at that frequency times the amplitude of your input signal. That will be this result, 0.449 volts. In a similar form, for a 3 kilohertz, 5 kilohertz, and 7 kilohertz, you will have this expression. So what you actually do is you multiply the magnitude, the input voltage amplitude at the associated frequency with the same frequency with the magnitude of your low-pass filter. So you do 0.5 times 1, 2 over pi times 0.705, etc. For the phases, what you do for the phase is the following. In order to calculate the phase of the output voltage, you need to calculate the phase of the low-pass filter and also the phase of the input voltage, and you add the phases of these two together. So that's actually the following. So at DC, the phase of your output, which is given by phase of the output at 0, which will mean DC, is the phase contribution of the low-pass filter at that frequency plus the phase contribution of the input voltage at that frequency. So in the frequency analysis expression, if you have a multiplication, that means that the phases must be added, and if you multiply this, then the magnitude will be multiplied. So that is the calculation. This is also discussed in a separate video about phasors and complex numbers. So if you want to know more about it, you can find that video also on this channel. What you see then, just again looking at our table, we can see at DC the phase of our input was 0 degrees. The phase of the low pass was 0 degrees, so you will have 0 degrees plus 0 degrees will be 0 degrees. So that is actually what you have at DC. The phase contribution at 1 kHz for the low pass filter, the first harmonic, was minus 45 degrees, and the phase contribution of the first harmonic at 1 kHz for the input voltage was minus 9 degrees. So I need to add these up, this is shown here, and I will have minus 135 degrees. Now, in similar form, 3 kHz, I have minus 72 degrees. At 3 kHz, I have for the input minus 9 degrees again, and I will add them up, and I will have minus 162 degrees. In a similar form, I can do it for 5 kHz and then for 7 kHz, and I have these results. So I have the phases and also the magnitudes associated for the DC and for the first 4 harmonics. Then I have this table generated. You can see the magnitude, the output voltage actually at the specific frequencies, and also the phases at the specific frequencies. So I can now generate the time domain representation of the output voltage, which will be given by this expression, which is pretty similar to this expression in a form that you look at the specific frequency and you actually use the magnitude and also the phase in the template function, which is the cosine of 2000 pi nt. Now, this is our DC value plus the amplitude 0.449, you get it actually from here. 2000 pi t, which is the fundamental, minus 135 degrees, which is the phase shift at that frequency. The next one is 0.067, shown here, cosine, and then the third harmonic, so 3 times this, 6000 pi t, minus, which is actually this phase. And then plus the next one, 0.025, and then I move on to cosine, and then I do 5 times the fundamental, which is 10,000 pi t, and then I use this phase. And if I move on to the next one, is 0.013, which is the final one in this table, and then cosine, and I will do 7 times the fundamental, will be 14,000 pi t and minus 172 degrees, etc. Of course, this will move on, but this is actually for the DC and the first 4 harmonics. It will already give you some idea how the waveform will look like. So let's look at the output signal spectrum. Again, this is the output signal we have just determined, and I look only to the first 4 harmonics including DC. So I have DC, as you can show here, and also the first 4 harmonics. You can see at DC 0 radians per second. This is the radians per second. This is the amplitude. So this is the amplitude spectrum. This is the phase spectrum. What you see is at 0 hertz or 0 radians per second, I see that the 0.5 here, that's actually from here, so that's output. Okay, I can also see that the amplitude is 0.449, which is this, and I can also see that the associated phase is minus 135 degrees, which is shown here. The phase at DC was 0 degrees, it's also shown here. Again, at third harmonic, you can see the amplitude, fifth harmonic, you can see the amplitude, and now for the seventh harmonic, you can see the amplitude. These are all shown here. So 0.067, 0.025, 0.013, all of them are here in the amplitudes. The phases, associated phases, you can also find here. What you see is the phase will approach approximately at minus 180 degrees if you move on with your harmonics to 9th harmonics and 11th harmonics. And if you move on with your harmonics in the amplitude, it will approach approximately the value of 0. So at some point, the harmonics will not contribute that much. That's actually for this situation. So if I now move on, and I will also like to know the total harmonic distortion. We will then total distortion for this circuit. So let's look at it for the input signal also. The input signal was given by this expression. If you just look at the DC and also the first 4 harmonics, the total harmonic distortion at the input will be given by this expression. What is the expression here and how is it calculated? It actually says the following. You collect the higher harmonics except the fundamental, and you will actually collect them in this way that the third harmonic, the fifth harmonic, and the seventh harmonic will be, the amplitudes will be squared, and then it will be added together, and it will take the square root, and you will divide by the fundamental frequency amplitude. That's actually what the expression says. Since of course the n is odd, you will have n 3, 5, and 7 for this expression. Of course you need to move on to 9, 11, etc. in theory, but at some point that will not contribute that much, and I have seen that the amplitude will decrease very rapidly. So the V in 1, that's amplitude, that will be actually this one. V in 3 will be this, V in 5 will be this, and V in 7 will be this. So if you just substitute the values, so this is this square root term divided by the fundamental frequency amplitude, I have this expression, and that will give me 0.414, which is 41.4%. That's actually what you have for your total harmonic distortion. Now, the total harmonic distortion for the output signal will also calculate in a similar form. This is our output signal. Again, we use the DC and then the first four harmonics, just to give you an idea. What we of course have is this input signal is applied to a low pass filter, so I expect that the total harmonic distortion will be less compared to the input. So we will see that. Again, in a similar form, we do that for V out for the first harmonic amplitude, and you will then calculate the square of the squares. You actually the squares of the third harmonic, the fifth harmonic, and the seventh harmonic, add them up, and you take the square root, and you will then divide that by the amplitude of the first harmonic. If you do the math, just using these three values for the harmonics and then divide by the first harmonic amplitude, you will have 0.162. So it is actually 16.2%. You can see that the decrease is definitely in place here. By using a low pass filter, you can decrease your THD, your total harmonic distortion, in this fashion. So this is actually what we also will verify in our simulations. So let's look at our simulations in SPICE. So the simulation results, as said before, this is the simulation we have done in SPICE. This is the circuit I have generated in SPICE. This is the Vin, the input voltage, which is this waveform, of course. This is the inductor, 400 millihenries, and this is our resistor, 2.5 kilo ohms. This is the input voltage measurement point, and this is the output voltage measurement point. The waveform again, and also the original circuit. This is the Fourier series of the input. What you see is I just started at sampling at 1 milliseconds because the first part of the signal is sometimes the transition, so that will be not really accurate for sampling. So you are most of the time start a little bit later with sampling. That's actually what I do here. The base frequency is of course our fundamental frequency. This is 1 kilohertz. The number of samples is the number of samples, as the name applies, the accuracy of your sampling. So I chose actually the largest one in this simulation. The number of harmonics I would like to know is the 7, because I go all the way to 7th harmonic, and I have the format like the amplitude and a cosine form with this frequency and also the phase, associated phase. This is for the input, and I've then used the initial conditions as given. In this case, this is an important note. The simulation will use the K actually as the N. So the N here is the K actually. I mean the K here is actually the N. So that's actually what we need to consider. So this is the Fourier series, which you can see the amplitude and also the phase. This is the 0. For K0 will be actually DC. That means the 500 millivolts is shown here. So that's correct. And the phase was 0 degrees. The first harmonic, that's actually this is just N. So N is 1. That is what we had also in our calculation. This is actually, if you do 2 over pi, you will get this result. That's actually the amplitude for 1 kilohertz or 2000 pi radians per second. And the associated phase was, in our case, in our calculation, calculation was minus 90 degrees. Of course, due to some numerical errors in the simulation, that will be of course very close to minus 90 degrees. Not exactly, but it is very close. The second harmonic, that's actually what we don't have in our output waveform, also the fourth and the sixth, so you don't have the even harmonics, you can see that the values are very small, approximately 15 or approximately maybe 15.4 picovolts, which is actually almost zero. Now you look at the third harmonic, you can see that this 211.84 millivolts, that will be again calculated using 2 over 3 pi. So if you do the math here, you can see that this will be very close to that value. If you now do also for the fifth harmonic, that will do 2 over 5 pi, and this will be 2 over 7 pi, and you will get these results. What you also see is that the harmonics here, total harmonic distortion, is 41.3% approximately. So let's look at our input, which was this again. This was 2 over pi again, this is this. 2 over 3 pi, this is this one. 2 over 5 pi, which is this, and 2 over 7 pi is this one. You can see also the phases, so it's minus 9 degrees, approximately minus 90 degrees, approximately minus 90 degrees, approximately minus 90 degrees. And the total harmonic distortion, as we discussed previously, it was 41.4 in our case, and this is 40.13 approximately. So it's very close to what we have calculated. Now, again, in a similar form, we have the output situation. So what we have is the Fourier series of the output. Again, we start at sampling at 1 milliseconds, and again the base frequency and the sampling number of samples, and I go to the seventh harmonic, and again in a similar fashion. Again, the K is here the N. So what you see is the output is almost 500 millivolts, so the input is approximately the output at DC, which is actually what we have. So if I look at my output expression, you have a 0.5 here, and if I look at the first harmonic, which is at 1 kilohertz, I can see that it is 0.449, and it is pretty close to what we have in simulation. The phase was minus 135 degrees. It's also really close to what we have in the simulation, which is actually minus 134.5 degrees. Very close to what we have. Now the next one, again the second harmonic, the fourth and the sixth harmonic are very small. It's approximately 30.9 microvolts, 7.51 for the fourth harmonic microvolts, and for the sixth harmonic it is very close to 5.1 microvolts. So all of them can be considered actually as zero. So that said, we can now look at the third harmonic, which is 66.71 millivolts, which is this, very close to actually what we have here. And the phase is minus 162 degrees here. I have here minus 160 degrees approximately. So again, due to numerical errors, we can see that this is also not really exact, but it is very close. So this is a very nice result. This is 25 millivolts, and I can see a 24.6 approximately millivolts. It's also very close, and the phase is minus 169 degrees, and I read here minus 166 degrees. So again, very close to what we have calculated. The last one, the seventh harmonic, it is 13 millivolts, and it is 12.5 millivolts. Again, very close to what we have. And this has a phase of minus 172 degrees, and this is minus 168 approximately degrees. So also very close to what we actually have. What you also see in the harmonic distortion is 16.04%, and we had really close to this value in our calculation. So we can see the simulations and also the calculations do match very well in the given numerical error in the simulations. So let's look at also in the real-time simulation how I did this. So that will be also very helpful. So let's jump to SPICE screen. So this is our SPICE simulation. This is our circuit. I have built the circuit again here. You can see this is the inductor of 400 millihenries. This is the 2.5 kilo ohms resistor. This is my input. This is my output node for the measurement, and this is my input. I have now, if I double click on this one, you can see that the square wave here is given, and I have a square wave amplitude of 0.5 volts, 500 millivolts. So I go 500 millivolts up, I'm 500 millivolts down. Of course, I needed amplitude of 1, just starting at 0, so I don't want a symmetric waveform. This will be done using the DC level shifting. This is actually shown here. and I also have the frequency of 1 kilohertz. What I also have is the rise and fall time in this waveform. That must be of course specified because there's no infinite speed, so it needs to be also specified. So I used very short value, which is 1 picosecond. Of course you can decrease this, but it's actually what I have chosen. So this is actually what I do. So you can also choose a different waveform. So I have just square. This is the amplitude, this is the frequency, and this is the rise and fall time. Okay, this is the DC level value, because if I do this 0, I will have a symmetric value. Of course, I won't have a value which is starting at 0, and I'll have an amplitude of 1, and then have a period of 1 millisecond. Okay, that's my value for the input. Now, if I go to analysis here in my SPICE, and I go to Fourier analysis, and I do Fourier series, I have then the following. This is actually what we have. So I have chosen here the input time for to have some accurate measurement. This is the base frequency, which is our fundamental frequency. This is the number of samples, so I can of course choose a smaller one. That will be of course less accurate. Of course, if you choose the larger number of samples, that will of course take some time to calculate it, but in this case it is very fast. If you of course go to very high harmonics, so larger harmonics, you will have of course a different more results. Okay, this is the expression I have. You can also have in a complex, you can also have an A and a B as shown in the general Fourier series. This is the RMS and also the phase, and this is the effective value of these two amplitudes, B, A and B. I have just chosen this one because it is very nice to see. If I now do this calculate, I can see again similar values, and I can see 500 millivolts and phases, etc., for my input. If I do this also draw, we can also draw this. I can say I want to have a drawing. This is actually what we have. So this is actually the plot, and it is actually a similar plot for what we have discussed also in the previous examples. What you see is the amplitude here. You can also make an auto label. So if I do here, you can see it is 0.5, and if I do here, you can see it is 2 over pi value. That's actually what we have. So if I just increase this, make that some larger values, so it's easier to read. Also this one. So you can see this is all clear. And if I now look at this for the phase, in this case, for the input, it was approximately minus 90 degrees, and you can see that it's correct. So this is actually the plot where you see the amplitudes and also the phases, and the base frequency is given by 1 kilohertz. I can also do this for the output. So I will go and then do Fourier series output and calculate, and this will be then our plot. Again, the total number of distortion approximately 16%, and these are the values, amplitudes, and also the phases. You can see that the second, fourth, and the sixth, these are the even harmonics, are approximately 0, very small, but the first harmonic, which is the fundamental, the third harmonic, the fifth and the seventh harmonics are there and as calculated. Again, if I press the draw button, I can also have a drawing of my output waveform. This is shown here, again very close to 500 millivolts. This is the next one. You can also do auto label here. You can see it's 449.49 milli, so it's approximately 490 millivolts. Again, if I make it a little bit larger, you can see that more easily. And also the associated phase of that one was minus 135 degrees. Again, you can see this. You can make it larger. You have this expression, and now we can see that the simulation also is very close to what we have calculated. We have discussed also in our previous discussion. Now you have also seen this in the real-time simulation, and that is what we have here. I hope this was clear for the situation here in using the simulation also. That will give you of course a lot of the background. So I see you next time, and take care.